All right. So now let's talk about freefall. That is, we're going to make two assumptions. One, acceleration is constant. And two, acceleration is specifically equal to the value 9.8 meters per second squared down. Again, we do need the down because acceleration is a vector. So, first thing I'm going to do is I'm going to say, let's just actually make the assumption that this is really, we'll just use one sig figure, and it will be 10 meters per second down. Just so we can get do the math in our head a little bit easier. So if we've got this situation, which is a pretty good model when things are close to the surface of the Earth and they are just out in the air and nothing's touching them, so long as air resistance isn't a big deal, what happens? So let's take a look. Say we have like a little ball or a stone or something right here. And when t is equal to 0, when we start the clock, we'll start our measuring tape there as well. X naught, our initial position, will be 0. And our initial velocity, that'll be 20 meters per second up. And let's go ahead and call up the positive direction. So this will be positive 20 meters per second. What happens 1 second later when t is equal to 1 second? Where are we? How fast are we going? Well, for these, we can go back to our constant acceleration equations that we wrote right here. So to find the initial, I should not have written in 0 there. To find the velocity 1 second later, we can use this equation. So our initial velocity is 20 meters per second. 1 second has passed and we have acceleration. It's 10 meters per second squared down. All right, well, so if up is positive, down must be negative. So that means our acceleration is really negative 10 meters per second squared. The negative and the down are telling us the same thing. So, velocity at 1 second, t equals 1 second. Put in our acceleration, our time, and our initial velocity, and we will get acceleration, that's negative 10 meters per second squared. Time is 1 second, and the initial velocity is 20 meters per second. So we will get negative 10 meters per second squared times 1 second. Well, that'll be negative 10. Negative 10 times 1 is negative 10. And then meters over second squared times seconds. One of those seconds will cancel, and we'll get meters per second, which is good, because we're looking for a velocity. And we'll add on our initial velocity, 20 meters per second. And we'll get 10 meters per second. It's positive, so that means it's going up 10 meters per second. Okay? How far has it traveled? Where is it? Well, for that, we're going to use this equation. Position at t equals 1. That'll be 1/2 times the acceleration multiplied by t squared plus the initial velocity multiplied by t plus the initial position. So that's 1/2 times our acceleration, which is negative 10 meters per second squared, multiplied by time squared. Our time is 1 second, so 1 second, quantity squared, plus our initial velocity. Well, we're running out of room, so let's wrap that around. Plus our initial velocity, which is 20 meters per second, multiplied by our time, 1 second, plus our initial position, and that's 0. So what do we have? 1/2 times negative 10. That is going to be negative 10 divided by 2, or 5. Multiplied by 1 squared. 1 squared is 1. 1 times 5 is still 5. Okay, so we're good on the numbers. And now the units. Meters per second squared. The seconds have to be squared, so multiplied by second squared. Ah, fabulous. seconds cancel. We're left with meters, which is good because we're looking for a position. So that's the first term. Next term. 20 times 1. Excellent. That's 20. Meters over seconds times seconds. The seconds cancel. We're left with meters. Again, great. Plus 0. We can do that. So now we've got -5 meters. Ignore all of this that canceled out. -5 meters plus 20 meters. That's going to be 15 meters. So here we're at 15 meters. So let's just draw the dot right there. Okay. Next second has passed. Where are we when t equals 2 seconds? What's our position? What's our velocity? Oh, and again, these guys are both positive numbers, so that means we are higher. We are up here, and we are traveling in the upward direction. Position's positive, that's how we know we're above 0 in the positive direction, and v is positive, so we are traveling upwards. Let's go ahead and write those arrows. So here we have a biggish arrow because we're going 20 meters per second. Here we're going half of that speed in the same direction though, so we'll draw an arrow that's half as big. All right, so let's go ahead and find speed. V equals acceleration times time plus initial velocity. The acceleration is -10 meters per second. Time is now 2 seconds squared, apologies. Time is now 2 seconds. And the initial velocity is still 20 meters per second. So now we have -10 times 2, that's -20. The units are meters over seconds squared times seconds. So we'll have a seconds up here. We'll cancel with 1, but only one of those seconds. So we'll be left with meters over seconds. Plus the next term, 20 meters per second. And we have -20 meters per second plus 20 meters per second. So we're actually stopped. We have no velocity up here, 0 meters per second. Okay, let's see where we are. Position. That's equal to 1/2 the acceleration times time squared plus the initial velocity times time plus the initial position. 1/2 the acceleration is -10 meters squared, meters over seconds squared, Seconds are 2 seconds, that whole quantity needs to be squared, plus the initial velocity, that's 20 meters per second, multiplied by the time, 2 seconds. So here's the first term, there's the second term, the third term, it's 0, so I'm this time not even going to bother writing it down. Okay, so let's multiply these first two. 1/2 times -10, that's -5 meters per second squared. And then I gotta square this whole thing. So I square the 2, it's gonna be 4. I square the seconds, that's seconds squared. The seconds squared cancel out again. Do the next term. This is 20 meters per second, that's our initial velocity, times 2 seconds, that's 40 meters per second times seconds. The seconds cancel, and I've got -5 meters times 4, that's going to be -20 meters, plus 40 meters, and I will be at +20 meters 2 seconds after I'm thrown. So in the first second, we went 15 meters up. In the second second, we actually only went 5 meters up. 1 second after we started, we were at 15. 2 seconds after we started, we were at 20. So the difference in that second was only 5 meters. So if this is 15 meters, then a third of that is going to be 5 meters. So we'll actually be in the second. We'll be right here. And we have no velocity, so I'm not going to put I'm not going to put an arrow on here. So we're traveling up. Maybe I'll give us a little more room over here. I'm going to copy these guys down. At 1 second, my position is 15 meters up. My velocity is 10 meters per second up. And what do you think is going to happen 3 seconds later? Where am I going to be when time is equal to 3 seconds? Well, first let me just box everything up so we can keep track of. There's when I start. There's t equals 0. Here's 1 second later. I'm 15 meters up in the air. My velocity has slowed down to 10 meters a second, though I'm still going up. 2 seconds later, nope, I did not write in the position, but I am at 20 meters up about where I started, and I'm not moving anymore. I've stopped, temporarily of course, but I don't have any velocity right here. 3 seconds later, where am I? Well, let's find position first this time. 1/2 times the acceleration. I'm going to go ahead and just plug that in. 10 meters per second squared multiplied by time squared. 3 seconds squared. Of course, I've run out of time, so we'll add on the second term right here. Initial velocity, that's 20 meters per second multiplied by time. 3 seconds plus initial position, that's 0 plus 0. And 3 seconds after I started, t equals 3. I got 1/2 times -10, so that's -5 meters per second squared. 3 seconds squared, so I square the 3, that's 9. I square the seconds, that's seconds squared. Second term, 20 meters per second times 3 seconds. 20 times 3, that's 60. Meters per second times seconds. The seconds will cancel. That's meters. So 3 seconds after I start, I am at -5 times 9. That's -45 units. Meters over second squared times second squared. The second squared cancel. That's meters. Good. We're looking for a position. Plus 60 meters. So -45 plus 60, that is positive 15 meters. So I've moved down. I was at 20 meters at second 2. At 3 seconds, I'm at 15 meters, which is actually the height I was at 1 second. So I'm right there, right back where I was at the very first second after I was thrown. All right, let's do velocity. Velocity is equal to acceleration when it's constant times time plus the initial velocity. Acceleration is -10 meters per second squared. Time is 3 seconds. Initial velocity is 20 meters per second. -10 times 3 is -30. Meters over second squared times seconds. One of the seconds canceled. I'm left with meters over seconds. Second term is still 20 meters per second. -30 meters per second plus 20 meters per second. Well, that is -10 meters per second. Units work. It's in meters per second. We're looking for velocity. -10. So negative means I'm going down. Up is positive, down is negative. But it's the same speed as it was coming up. So same size arrow, just in the opposite direction now. And what do you think is happening 4 seconds after you're thrown? So here we are 3 seconds later. Well, we can actually do this now. You'll notice that every single time, every second that passes, our velocity is changing by 10 meters a second, which is of course exactly what it should do, because acceleration, which by definition is change in velocity per time, is 10 meters per second. So every second that goes by, we should change by 10 meters a second. So I can actually write down 4 seconds later, we're going to be another -10 meters per second than we were 3 seconds into the throw. So this is going to be -10 meters per second minus another 10 meters per second, or -20 meters per second. And our position, well, you may have noticed these positions are the same, and so these two positions here are also going to be the same. We're going to be back at 0 again, just traveling in the opposite direction at the same speed. Fabulous, I have one more color. So this is what happens in Freefall, where you really can model it well, as the acceleration truly is well modeled as a constant, and moreover, it's well modeled at this constant. 10 meters per second squared when we're doing things just in our head without a calculator, or when you've got a calculator, you can go ahead and use 9.8 meters per second squared down. All right, so this is how Freefall works. Every second that passes by, you lose about 10 meters a second of velocity, or you go 10 meters a second more downward. If you were starting going upward at 20 meters per second, 1 second later you're going 10 meters per second upward, 1 second after that you're not moving, 1 second after that you've gone to 10 meters per second downward, and a second after that you've gone to 20 meters per second downward. It's a little harder to do the position in your head, but essentially what you're doing is you're doing the average velocity of the velocities. So the average between 20 meters a second and 10 meters a second, that's 15 meters a second. And 1 second passes, so if you started at 0, you've gone up 15 meters. Here, the average velocity between 10 meters a second and 0 meters per second, that's 5 meters per second. So 1 second after you're here, you've gone up an additional 5 meters. So if you were at 15 meters, you've gone up to 20. And then on the way down, well, 0 and negative 10, they average out to negative 5. So you will have, after 1 second, dropped 5 meters from where you were here. So you've gone from 20 to 15. And then here you've got velocities negative 10 and negative 20. Those average out to negative 15. So you will have dropped 15 meters. Oops, I wrote that as seconds. That's no good. You will have dropped 15 meters 1 second after you're here. So in this case, you'll get down to 0. Now, when is this a good model? I said it was a pretty good model when you're near the surface of the Earth and you're dropping things and you don't have air resistance. So this won't work very well for things like pieces of paper or feather, where air resistance is important. They'll work pretty well for things like baseballs or, small, compact, sort of dense things. But it turns out that this is not absolutely true. In other words, acceleration isn't really this value at the surface of the Earth, nor is it constant. Acceleration, due to gravity, changes depending on your altitude, really depending on how far away from the center of the Earth you are. So if you go up on a mountain or you go down into the bottom of the Grand Canyon, you're going to have a different acceleration if you are falling through the air. It also turns out to depend on your latitude, how far away you are from the equator. You're going to have a different acceleration depending on whether you're on the equator or whether you're at one of the poles. But this is still a good model. Even though it's not 100% accurate, it is accurate enough for us to do many of the calculations that we do. So this is the model we use, even though we know that it isn't 100% true to reality. It's good enough.